Okay, hello everyone. So, okay, for this one, so let me just go bigger. Okay, so all right. So here is another sharing section. So basically, this again is just I just summarize all the topic, all the small topic. It's a very high level in this recording so that maybe it will help you to gain a bit understanding or to help you understand a bit about this software securities, okay, about this topic. So again, how the approach I'm using is I trying to summarize all the topic, subtopic, and so on, and then I make use of the AI, and then come up with this summary notes. So, all right. So, without any furthermore delay, so let's go through this software security. So, again, this is a bit also a bit dry. So, because my intention is this is should be some summary, like a summary. All right. So, let's go. So, in this topic, so we will get to know about software security, the flaw, the bugs. Okay, so it can be the design flaw. So this occur when the design of the software does not meet security requirement. Okay, for example, the weak cryptography, or you did not follow certain design principles, some programming rules, and so on. And also there is some called implementation flaws. So error in the code itself, logic, some error handling, buffer overflow, poor input validations, and then the attacker can be exploited. Okay, so the attacker objective always like they typically aim to gain unauthorized access, escalate privilege. They want to get the admin rights. They want to do more things, or just simply like crash a system by exploiting the vulnerability like buffer overflow. Okay, so in order to understand this topic, there is some so-called fundamentals knowledge needed in a subject called data structures. So, and then we need to study a bit about the operating system. So one of the topic here is like memory layout. So the memory is running a program divided into several sections. So the data, the text, okay, the text contain the executable code. The data store global and static variables. The heap grow upward and is used for dynamic memory allocations. For example, malloc in the C programming. Stack go downward and store function called data, local variables, and return addresses. So the example here is that when a function is called, its parameter and the local variable are stored on the stack, and when the function return, the data is removed. Okay, so and then next stack and the function call. So we need to know about stack frame. So when a stack is called, a new stack frame is created containing the function argument, the local variable, and then the return value, the instruction to return to after function finish. Okay, so function call process. So arguments are pushed on to the stack in a reverse order. The function is executed. After the function finish, the stack pointer move back to the caller function frame. Okay, then we need to learn about memory allocations. So stack used for local variable and function call data. It has a fixed size and growth downwards. Okay, heap used for dynamic memory allocation and grow upward. Okay, the programmer is responsible for managing the heap memories. Right. Another term, buffer overflow. So occur when a program writes more data to a buffer memory space that it can hold, leading to overwriting adjacent memory. So, for example, if a program have a buffer to store 4 character but write 8 character, the extra data could overwrite important information like return addresses, allowing attacker to take control. So put it to the simple, another simple example is like you have a glass and then you have water. So you pour the water inside the glass. But if you keep pulling, if it's full and then it's good, become overflow, right? So the water will be coming out. So this is another examples that you can relate to this buffer overflow. So the real world incidents that you can Google a bit like about this code red happened in 2001, a buffer overflow in Microsoft IIS, the web server, I guess, allow remote code executions. And then for another one is heartbeat, okay, heartbeat 2014, a bug in OpenSSL allow attacker to read more data than intended from the memory. Okay, heap overflow. So occur when buffer in a heap are overflown, potentially corrupting data structures like function pointer and leading to arbitrary code executions. So buffer in the heap are overflown, potential corrupt the data structure itself. Okay, so function pointers and code injection. So function pointer, if function pointer are overwritten in the buffer overflow, an attacker can make a program execute their malicious code. Okay, if your function pointer are overwritten in the buffer overflow, the attacker can make the program execute their own code. Okay, code injection. When the attacker inject malicious code into the program and override the instructions pointer, the injected code run instead of the intended program. Meaning you inject the code into the existing program and then override the instructions pointer. So this injected code, it will be trigger lah, it will be run. Okay, so mitigations for memory vulnerabilities. Okay, stack canaries, special value placed near the return address. So if a buffer overflow occur and changes the canary value, the program detect it and crash before further damage. Okay, non-executable stack, prevent code execution from the stack, making code injection harder. Okay, another one ASLR, address space layout randomizations. So randomize the memory locations of variable, making buffer overflow and code execution less predictable. Okay, so all these things you might Google and then you can try to read more to understand how these medications can be handled for these memory vulnerabilities. So, and then we have integer overflow. So, occur when arithmetic, mathematics operations produce result outside the allowable range. Okay, potentially leading to incorrect memory allocations. So, for example, if an integer overflow result in malloc, okay, malloc functions no memory will be allocated, so causing potential buffer overflow. Okay. Now pointer dereference. When a program tries to access a pointer that is now point to nothing, it can crash the program or be exploited to bypass security checks. Right? So format string attack. When user input is directly used in a function like a printf, okay, print some result out, okay, it can allow attacker to read or write arbitrary memory by manipulating format string. So example, printf user input can be dangerous if user input is not sanitized okay, as an attacker could input percentage X to print memory addresses. So instead of just printing some string, some output, he print the memory addresses. Okay, so here that is one of the step-by-step breakdown lah, about the stack and function call. So the stack is a sections of the memory used for managing function call and local variable. It operates in the LIFO, okay, last in first out manner, meaning the most recently added data is removed first. Each function call create a stack frame. Okay, function call process, okay, step by step. Before function call, when a program start, okay, a main function runs and begin adding its data to the stack. At this point, a stack pointer, percentage E SP, okay, the stack pointer SP, okay, percentage E, okay, SP in 32-bit lah, easy point to the top of the stack. So calling a function. When a function is called, several steps happen. Arguments push onto the stack. Before the function start, the arguments are pushed onto the stack in reverse order. For example, if a function is called like this, function, okay, argument 1, 2, 3. So the order on the stack will be like this. Okay, you can from the top to the down is 3, 2, 1, something like this. Return address. The address of the next instructions to execute after the function finish is also pushed onto the stack. This ensures that the program knows where to return after the function is complete. Okay, now entering the function. Once the function start executing, the stack change as follows. Stack frame creation. A new stack frame is created for the function local variables. These are stored on the top of the arguments that were pushed earlier. Frame pointer E percentage E BP, okay, setup. Okay, the base pointer, okay, BP is saved onto the stack and updated to point to the top of the current stack frame. This is done to keep track where the function local variables are located. Okay, local variable push. The function local variable are now pushed onto the stack. For example, if the function declare local variable, local, okay, for example, under the function that is integer, LOC1 or character LOC2 with 4. Okay, this can be the array. Okay, 0, 1, 2, 3. Okay, stack will look like this. Okay, this is your base pointer. Okay, return address argument 2, 3 local variable 1 okay, int local the LOC2, okay, the local variable array, another one. Accessing local variable. Local variable are accessed relative to the base pointer, percentage E BP, okay, for instance, okay, LOC1 will be located at some offset of percentage EBP, for example, -4, examples, percentage EBP, since it is a 4-byte for integer. Okay, log2 might be located at -8, okay, 8, okay, percentage EBP, because it's for byte. Okay, so function executions. During the function executions, the program perform operation on the local variable and parameter. The stack pointer, percentage E, SP, always point to the top of the current stack, so it keep changing as a variable are push or pop. Okay, then function return process, clean up the stack. When the function is done executing, it has to clean up its stack frame and return to the caller. So here how it happens. So local variable pop. The local variable are removed from the stack and the stack pointer percentage ESP move back to the location before the function call. Frame pointer restore. The save old frame pointer percentage EBP is popped from the stack and restored, meaning the base pointer go back to what it was before the function was called. So return address, the return address is popped from the stack and loaded into the instruction pointer percentage EIP, which tell the CPU where to resume execution. This return address point to the instruction after the function call. So back to the caller. Once all these function return, the program continue executing at the location specified by the return address using the stack frame of the caller functions. Okay, so now stack and function call diagram. So imagine a function, okay, function is called from the main. So before call, the stack hold data for the main function, including its local variables. During the call, while inside the function, the stack grows and arguments are pushed and the return address is stored and the function local variable are added. After return, the stack shrinks, okay, as the function local variable, frame pointer and return address are popped. Then program resumes back to the main. So these are some of the key points to remember. Stack frames are created for each function call, storing argument, local variables, and the return address. The base pointer percentage EBP keep track of the start of each stack frame. The stack pointer percentage ESP always point to the top of the stack and move as data is pushed or popped. Overflowing the stack. In a buffer overflow, can overwrite the return address, leading to potential security vulnerability like code executions. Okay, so with this, it should summarize, give you some ideas on this security, software security. Okay, so because of this, there are some of the, like for example, like this is another, like the example used in the for the heap overflow. So my understanding is like I'm trying to also like make use of the AI to help me to generate more understanding, like how could what is the problem in this C programming code, and how to do the corrections and so on. Like for example, this is the code like type definition structures, okay, vulnerable structure, okay, char buff max length, okay, integer, this asterisk CMP, okay, char asterisk vulnerable, integer full, okay, vulnerable. So all this uh, uh, the code. So trying to understand it, like for example, um, because this is a code snippet, right? So that's why the max length is not defined. The string copy function override the buffer twice. So you might need to concatenate or avoid overwriting the first string. So some of the headers maybe because this is just a code snippet lah. So after that, there is some corrections. So I not tested the code. So again, this is just for some sharing. So it could be wrong, but this is just for the sharing purpose lah. Like for examples, like you need to add this string as a header because it's needed for the string copy. You need to define the max length, like for example 256 for the length, define the maximum length for the buffer. And then if we need to buffer with define size, because now we define already. So here is better. So function pointer for comparison. So this is for the comparison, okay? Then we go for this code. So ensure you don't overwrite the buffer. You want to concatenate. Okay, so for example, this the code lah, number one and max length -1. So copy first string, ensuring no buffer overflow, and then again string cat. Okay, follow this. This is second one. So you use the max length minus the string length. So you can see concatenate the second string and then return as compare, okay, string buffer and call comparison functions. And this one no nothing, okay, this one no need. So the key changes here is that we define the size for the buffer. We use string c copy and then the string cat. So this function prevent buffer overflow by limiting how much is copy and concatenate into the buffer. Because if you look at here is string cat, string copy, string cat. So this is different. This is string and cat, string and copy, something like that. So this version is safer and allow potential buffer overflow issue, ensuring that string operation respect the buffer limit. So this is the example code for the heap overflow for understanding lah. So then the next one is the integer overflow. Okay, integer overflow. So based on the code here, so you can see that this is the code void one above char response, then integer n response, packet get integer. If the number of response bigger than 0, response equal to matlock. Okay, number of response times the size of the char. Okay, for then a follow for I equal to 0, I smaller than number of response, I plus. So the response I packet get string now. Okay, so there are several issue. Okay, again missing header because this is just a code snippet, so it is definitely missing. So incorrect use of the malloc. So temporary allocation should be size of char rather than size of char. So there is a bit difference. Okay, since you are allocating the memory for the character array, not an array of character pointers. Okay, I is undeclared, the loop variable I is not declared, so no free call. Okay, free up the memory. The allocated memory is not free, so which will result in a memory leak. So function signature for packet get integer and packet get string, so these functions are not defined. So assuming they return appropriate type, then we can proceed without their implementation for now. So this is the correct code. You added back the library for the matlock, and then assume this function implemented elsewhere. Assume, okay, assume. So this is the one. Then this is the code itself lah earlier. So you declare again for the I. Then this is assume the packet get integer return the number of the response. So if number of response bigger than 0, allocate memory for number of response character, not the pointer. So here you use size of char, not char asterisk. Okay, if response equal to nothing, handle the matlock failure. Just print out standard error, memory allocation fail. Okay, else okay, fill in the allocated memory if the string, assuming the packet get string return a char. Okay, assume. So for I equal to 0, I smaller than the number of response, I plus. So response equal to the packet get string, nothing. So after you finish everything, you free up the allocated memory. Okay, this one you just ignore. Okay, so corrected the matlock. You allocate memory for the n response character using the size of char. Declare I. Added memory free. Okay, free up the memory is important to avoid the memory leaks. Error handling. Added the check to ensure the matlock doesn't fail. Okay, if it does, an error message is printed and the function return early. Okay, the corrected version should resolve issue regarding the memory allocations, available declaration, and then a proper freeing the resources. Okay, then the next one is the read overflow. the read overflow. Okay, so this read overflow, this I managed to follow lah, to follow for this. So this is the code. um, I type it, okay, because it's just using the one main function, right? So I type uh, is in the one of the online tools. Okay, one of the online tools I just type. So here, if you run the code, so the first thing when it print, right, so it will like he give you like he like print out the value, okay, the value of your buffer. Then you put in your data. So for example, like here is 26, right? So I'm getting 24 here only, like 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 24. So another two, he will be filled up by the dot. Okay, he will just repeat the buffer size, and then he print something like this. Okay, so he get the size of the buffer from the standard input output that it store in the P. Okay, then here, if let's say you put 38, then you just type this how to say, your string, your data, and eventually it's within the buffer lah, so you get another dot. Okay, let's say you type another 38 here, but your data is lesser than the allocated buffer. So you can see that the buffer is like reuse whatever left out from the memory. So this is what he trying to say. Like for example, you just put like 10. Okay, then you just uh, put something like 1 2 3 4 5 6 7 8. So you will see there another is the dot. Okay, like for example, now you define like how to say, you define 10 again, but then you put 1 2 3 4. Oops, I think he can't handle already. Eh, so this is something bad. Okay, let me just run again. Let me run again. So let's say I just declare like 10. Okay, then I put 3, for examples. Let's say, okay. So you can see 1 2 3 4 5 6 7 8 9 10. So if let's say I put 10 again, but this round I just put Monday. Okay, then you can see that he will refill it from dot, and then he will try to uh, uh, reuse whatever left over from the memory. Okay, can can follow. So the earlier the okay, what is written here is like, okay, this is the code. Okay, this is the output. Okay, so if we go back to here, let's say this is the corrected one. Like for example, um, he said in incorrect to use the atoy, and then potential buffer overflow. LEN might assist the buffer size of buff 100, potential causing undefined behavior. No bounds checking on the LAN for the follow does not ensure that I smaller than LAN stay within the size of the buff. Okay, so here is the corrected one. So like you need to put for this standard library.h for ATOI, right? And then here you need to add check if the input is null. Okay, then convert input to integer. Okay, then you get string input. So here then if check if the input is null, ensure that does not exceed the buffer size. So here, okay, it's modified already. Then print character, replace the control character with dot, something like this. Okay, so just now I testing it, so it should work. Let me just give a try again now. So you just remove it. Let's give a try. So earlier is 26, right? So Monday computer, let me see, security samples. Okay, that is if you calculated here, it should be 25 lah, then with one dot 26. So now if you type like the 8, so you can see secret password is awesome password 123. Okay, let me see, is it work? Oh, no, I think this password 123. Oh, is something not correct already. Okay, sorry, apologies. I think awesome. So I think I have to let me see this, double check again for this demo. Oh no, secret password is, let me just try one time. Let me just try one more time. 26. Let me try one more time. Okay. 28. Okay. Secret password is awesome as one catcher. This time is work. So if I repeat again 38, I just say short string. Okay, now it's working. Earlier I don't know why. So with this modified code, so you can see it don't have the he clear out the leftover data or the things in the buffer. So he is not doing like earlier. Okay, if if let's say if you get the code again. Okay, so this is the code earlier. Let me just copy. If let's say if you run this code, so the same thing if you do this is just examples. All right, 38 secret password is okay. Now if you do 38 again, short string here, can you see? So this is the earlier the code without without clearing the whatever leftover in the buffer. Okay, this is the code. If you clear out the buffer, okay, you print character, yes, then you replace. So with this better control, so it won't show already. Okay, so let's go back here. So here is like the key changer is like the toy and input validation. Use toy to convert the first input line to the integer while ensuring the input is properly checked. bound checking on the length added to check ensure length does not exceed the buffer overflow buffer size and prevent buffer overflow. Null termination safety for for loop ensure it does not go past the null terminator if the length exceeds the available string length. Control character replacement. Control character and replace with a dot as per your original code, but only if they are valid within the buffer bound. So this version allow potential memory issue while preserving the intended functionality. So well, okay, I think with this, I hope give you a little bit more insight on what we study on this chapters. Okay, with this, thank you so much and thank you for your time. So I'm going to stop